Welcome to this lecture on process control, chapter on Laplace transform, forcing functions. In the last class, the last lecture, we have seen one forcing function, that was step function. These forcing functions are used to describe the behavior of input variables after some disturbance occurs there. In other words, they are used to describe the disturbances in the input variables. Last class we have seen step function, and today we will see what is known as pulse function. We'll see pulse function. What is a pulse function? So here I have given some values. That is f of t equal to 0 for a period t less than 0. And then for a period t greater than 0 but less than h, that is for a period between 0 and h, the value of the function is a constant m. M is a constant. Then after h, t greater than h, after a period of t equal to t greater than h, the function value is 0. So h is a finite time period. Can you visualize this function? Can you make a sketch of this function? That is where the function is m during a time interval 0 to h. Except at this interval, the value of the function is 0. So can you make a sketch of this function? So this is the sketch of these values. This is a sketch of these values. For clarity, I shifted the 0 here. So this is 0. So 0 is here on the x-axis. X-axis is t, y-axis is a function. So 0 on both x and y-axis I shifted slightly for clarity, that's all. For clarity of this function, that's all. So f of t equal to 0 for t less than 0. T less than 0 is this period. T less than 0 here onwards, the value of this function is 0. And at t equal to 0, the function rises to a constant value or increases or changes to another constant value m and remains in this period up to a certain time h. At this time h, it very suddenly or very quickly or instantaneously returns to the original value, which is 0. So except during this period between 0 and h, except during this period, everywhere else the function value is 0. Only during this period, during a finite interval between 0 and h, the value of the function is m. So this is what we call as a pulse function. So these are the values and this is the sketch of the function. Now we require equations to describe this function. We require mathematical equations to describe this function. So we are not very much concerned with t less than 0, what has happened before t0. So our concern in process analysis will be what happens after 0 time. So we require equations for these two periods. Now if you take this first period, that is between 0 and h, if you see here, between 0 and h, between 0 and h, between 0 and h, this is a simple step function which we have discussed in the last class. Between 0 and h, this function is a simple step function. It rises from 0 to another constant value m suddenly at t equal to 0. So that fits the definition of a step function. So this is an equation of a step function will represent this function between 0 and h. For the time interval between 0 and h, the equation is simple step function. So the equation is f of t equal to m into ut, and its Laplace transform. What will be its Laplace transform? Its Laplace transform is going to be f of s equal to m by s. So for the period t between 0 and h, the equation is f of t equal to m into ut, and the Laplace transform is m by s. Now we require an equation for this period, that is for t greater than h. For t greater than h, for this period we require an equation. So even though the numerical value is 0 for t greater than h here, that is for this portion, the numerical value of the function is 0, but we need an equation which is going to give us the effect of or the history of this function, because the function is not 0 forever. The function has undergone two changes. From 0 to m, it has changed from 0 to m at t equal to 0. It has remained there, and at t equal to h, it has come back to the original value. So even though the original value is the value of the function is same as original value 0, we need an equation which will incorporate this history of this function into that value. So we'll look for that equation, and we will write what is that equation that is going to describe this value, or that is going to describe this function for t greater than h. Now, to get an equation for the period t greater than h, look at this sketch. I had drawn two functions. There is one function here which I have drawn this red line, and there is another line I have drawn here which is green. So I have drawn two functions essentially. So let me take it as take this as f1, this function as f1. Let me take this function as f1, and okay, I'll take it as, and this function as f2. So f1 is this function, this is f1, and this is f2. This is f2. Now focus on the period time greater than h, that is this portion. Focus on the period which is this period, time greater than h, here from h onwards. H onwards, after time greater than t greater than h, we know the value of the function is 0, right? So this is the value of the function for time t greater than h. But what will be the equation for that? So can we get an equation for this value from these two graphs, from these two functions? I repeat, can we get an equation for this value from these two functions? Our value is 0. We need to get 0, right? For t greater than h, we need to get this value 0. So what will be that? So that will be simply f1 minus f2, right? So f1 minus f2 for the period t greater than h is going to give me this function 0, right? For a period t greater than h, this f1 minus f2 is going to give me this function f1 minus function f2 is going to give me the required value 0. Clear? This f1 minus f2, because for t greater than h, f1 value is what? M only. For t greater than h, f2 is also m. Both f1 and f2 are m. Values of f1 and f2 values are m for this period. So f1 minus f2 is going to give me 0, which is this. Now let us write the algebraic equation for f1 and f2. You know f1 is what? If you see f1 is a step function. This f1 is step function u of t. If f1 is step function u of t, what is f2? So f2 is same step function, but its origin is not 0, but origin is shifted to h. So f1 is a step function starting from 0. f2 is also a step function starting from h. Followed? I repeat, f1 is a step function starting from 0. This is f1. And f2 is also a step function starting not from 0 but from h. So f2 is step function starting from h, f1 is a step function starting from 0. So what will be the equations for f1 and f2? If f1 is a step function, equation of step function is u of t. And f2 is also a step function, but it is shifted from 0 to h. So that is going to be what? If this is u of t, this is going to be u of t minus h. Followed? And there is a magnitude m, so we multiply by the magnitude m. So this is the equation for the period t greater than h. I hope it is understood, because f1 is equation for f1 is step function u of t. f2 is also step function, but origin shifted from 0 to h. So it is u of t minus h. Translation of function. And this is the equation for t greater than h. For t greater than h, so this is the equation. And what will be its Laplace transform? Laplace transform, if you take Laplace transform, what will be Laplace transform? F of s equal to step function. We know Laplace transform is 1 by s, and this is translational function. What is the Laplace transform? 1 by s into e power minus hs. So this is the Laplace transform of this function. So this pulse function will have two equations, one for the period lying between 0 and h. So in this period, it is a simple step function equation of a step function f of t equal to m into ut. F of t equal to m into u of t, and its transform is this m by s. For the period t greater than h, it will be given by difference of two functions, namely u of t and u of t minus h. So for t greater than h, the equation of this pulse function is this. Equation of pulse function is this. M into u of t minus u of t minus h. F of t equal to m into u of t minus u of t minus h. And its Laplace transform is this. So this is the meaning of, this is the equation, values and sketch for the pulse function. Now practically, how do you visualize this, or how do you explain this for an input variable? So when can it happen? So when can you describe the disturbance in input variable as a pulse function? When can you describe mathematically the disturbance in the input as a pulse function? Suppose the value of the function, value of the variable suddenly increases from one constant value to another constant value at time t equal to 0. Suddenly changes from one constant value to another constant value at t equal to 0, remains there for a certain period of time h, and then instantaneously or suddenly returns to the original value. So this is called the pulse function. So if an input variable behaves in such a way that it suddenly changes from one constant value to another constant value, remains there for a certain period of time, certain period of time interval, and then suddenly, quickly or instantaneously returns to the original value, then it can be described as a pulse function. So from these explanations, how do we describe a pulse function? Equation wise, values wise this, equations wise this, but physically, to understand it easier, to understand it so that we can find out which is a pulse, which we can later on identify which is a pulse function. So we can state as follows. So pulse function is one which changes from one constant value to another quickly or instantaneously. Instantaneously is a better word. Remains in this value for a finite period h, and then returns to the original value or quickly or instantaneously. Instantaneously or instantaneously. Both the changes from initial constant value to the initial constant value to the new constant value, and then returning to the initial constant value, both are instantaneous. So this is called a pulse function. I hope I had made the pulse function and the equations clear. So this in many processes, the disturbances in the input variables can be modeled by this equation. Some increase for some period of time, some variable changes for some period of time, and then returns to the original value. Okay. So the last class you have seen step function. There the change is permanent. Initial constant value to find the next constant value, new constant value is permanent. But whereas here the change is not permanent. It comes back to the original value after a finite period of time. Okay. And another point I want to make here is, I want to tell you that even though we had both in the last case step function and here we are considered one constant value to another, means we are considered the function increases from one constant value to another constant value. They are equally applicable if the function decreases from one constant value to another constant value. For simplicity, we are taking that function change as increases from one constant value to another constant value. So the equations are equally applicable if there is a decrease from initial value to the new final value. Okay. Hope you have understood this pulse function, concept of pulse function, and the equations for the same. If you have any doubts, please leave it in the comments. And I also request you to subscribe to this channel so that you will get to know the release of subsequent lectures. We'll be seeing more forcing functions in the next few lectures. See you.